we were talking sound as the primary example of longitudinal mechanical waves. So when we looked at one-dimensional longitudinal mechanical waves, we saw that the physical example of this was sound propagating through a straight windpipe, infinitely long and all that. So just to quickly reiterate the equation and formula and all that, we saw that in this type of wave, the medium through which the wave is propagating, the one-dimensional medium through which it is propagating, is nothing but the air inside a long horizontal air pipe like this. Okay, so this end of it is x equal to 0, and the other end is very far away, so it's extending to infinity. So at any general point x equal to x, okay, so if we create a longitudinal wave by creating longitudinal vibrations at this end, by putting a tuning fork in place and making it vibrate, or maybe we could attach a small diaphragm over here. Another way to produce this kind of wave would be at the end of the pipe here, we will place a diaphragm like that, and let's say we'll attach the diaphragm to a spring. It becomes an oscillating spring mass system. And as the diaphragm oscillates back and forth like this, it displaces air back and forth like this. And then the air next to it displaces. So whatever kind of source we have got, but the source is basically something which is creating simple harmonic oscillations of the air particles at x equal to 0 along the x-axis. So then that becomes the longitudinal displacement. So at x equal to 0, if the displacement is now some amplitude into sine omega t plus some phase constant, where omega is 2 by f of the source, then the wave propagates along this medium at a uniform speed that is a function of the physical properties of the medium. So in the case of gaseous medium, it is square root of gamma RT by. So then at a general point x equal to x, the displacement becomes a function of x and t. So this is the longitudinal, it is along x-axis. That's the longitudinal displacement of medium particles as a function of position, that is a mean position at x equal to x for any particle, as an instantaneous quantity at time. So longitudinal displacement. So that as a function of xt becomes whatever amplitude into sine omega into t minus x by v. Okay, because the wave will reach here after a time. If it started from here at t equal to 0, the oscillation will reach here after a time of x by v. So the time factor is affected this way. So when we generalize this, we see the equation of the wave becomes t sine omega t minus kx plus 5. So it's just like the wave equation in terms of transverse displacement y equal to a sine omega t minus kx, which we've seen earlier. But just that y is replaced with s, because now it is a displacement along the x-axis. So we sometimes also write this as s naught, because it's instead of t, the amplitude is written as s naught. Whichever notation we are using, a or s naught, whichever, that is the longitudinal amplitude, longitudinal displacement amplitude. And k here becomes omega by v, which then becomes 2 pi by lambda. So then we have v is equal to f lambda, where v is square root of gamma RT by m, or if it is a fluid medium, like a liquid medium, it is this speed of sound in a liquid, or if it is a solid medium, then it becomes square root of Young's modulus divided by density, a solid medium. But in a gaseous medium, assuming the gas is more or less like an ideal gas, okay, this is speed of sound in gas medium. And then we understand in this that V is the property of the medium, whereas F is the frequency of the source. It is independent of the medium, and the lambda is affected by both and others. Okay. So this is the starting point we saw. So this is the general equation, so to speak, of the longitudinal one-dimensional harmonic wave. General equation of one-dimensional longitudinal harmonic wave. And then we saw that associated with this, so what is happening is now if you consider any pocket of air within the tube or within the pipe, the two boundaries of that pocket of air, they are both vibrating back and forth like this, but they're not vibrating in phase. They are having the same frequency, but they're not vibrating in phase. There's some phase difference between them. So alternately, the air in between them is getting crushed and then rarefied, and then again compressed and rarefied. So section of the tube consisting of a certain amount of air will continuously get compressed and rarefied. So then we saw that by applying the principle that Bulk's modulus of elasticity is mod of delta P divided by delta V by V. Or in case of gaseous medium, we write it as dP divided by dV by V. We saw that the pressure variation or volume stress at a particular point, which we can write as P as a function of x and t, it becomes minus of beta into dV by V, which is the volume strain. So volume stress is Bulk's modulus into volume strain. So we saw that that becomes minus of beta into the area of cross section multiplied by del S by del S. This kind of thing. S is equal to S1 sin omega t minus kx plus phi kind of thing. So it's also the it's just like this. So this becomes the relationship between them. With this we see that it becomes beta k into S0 into cos of kx minus omega t plus phi. So this is the volume stress, the excess pressure, so to speak. You can see that for a displacement wave, for the longitudinal displacement being given by this kind of equation, corresponding volume stress or pressure can be represented by this kind of pi by 2 phase difference. So this becomes what we call the pressure wave. Here we have to understand that E, it is the volume stress, it is not the absolute pressure, it is the excess pressure. So it is the change in pressure at x equal to x at time t equal. So E naught is this pressure amplitude, and that is given by Bulk's modulus of the medium into k, that is 2 pi by lambda, into the displacement amplitude. So there is this relationship, and we understand that if P is greater than 0 at x equal to x at time t equal to t, that means there is a compression at that position. And if P is less than 0 at certain position, then there is a rarefaction. So any region or any point inside the air windpipe experiences alternate compression and rarefactions at the same frequency f at which the medium particles are oscillating. And that variation in pressure is periodic with respect to position, or it's a repetitive pattern with the same wavelength as the displacement waves. So that is the relationship. I think this is what we had This is the point we had discussed up till in the last lecture, and of course we had visually understood this phase difference of pi by 2 between this. So having done all that, now we will continue ahead with the next property of sound wave, which is the intensity of the sound wave. So intensity of a sound wave is defined as, actually intensity in general, it's a term used in wave mechanics. It is defined as the power per unit area, or you can say that the energy propagated per unit area per unit time. Yeah, Durgesh has screwed up. So that is the quantity intensity. So it is measured in watts per meter square. It can also be understood as the power propagated per unit area. That's also another thing. Yeah, so I'll come back to this. We'll just scroll up for a moment. This is the part you wanted to go over again, Durgesh.
Yes, sir. Done, sir.
So we'll have a similar method of calculating the power per unit area, or the intensity of the sound wave. Similar method as we had seen for calculation of power propagated through a string in case of transverse waves. Only there it was just the power propagated, it was not per unit area. One slight difference in that sense. So if this is again a windpipe through which sound waves are propagating, causing longitudinal oscillations of the medium particles. This is traveling with a speed v, and the displacement of the medium particles is represented by that equation. S is equal to S naught sine omega t minus kx plus. So if we consider a section of this medium like this of length dx, and the cross sectional area is A. So A is the cross sectional area. So for a section dx, sorry, dx, the mass of air present, that is going to be density into area of cross section into dx, and this mass has maximum kinetic energy of half dm into s naught square omega square. So how do we understand this again? Because again you can see that this is the displacement of the medium particles along the x-axis. So particle velocity. Now this time the particle velocity is also along x-axis. The particles are oscillating along the x-axis. So that is given by del s by del t. That becomes s naught omega cos omega t minus kx plus 5. So accordingly, you can see that the particle's velocity's maximum value is also s naught omega, because after all it's an SHM with an amplitude of s naught and an angular frequency of omega. So maximum this thing kinetic energy is this much. So therefore, average kinetic energy will be half of half dm s naught square omega square. And average kinetic energy will be equal to average elastic potential energy because of the stress and strain. So each will be 1 by 4 dm into omega square into s naught square. So the energy, the mechanical energy of that section, this is the mechanical energy of oscillation for the section dx. That is now becoming the sum of these two, average kinetic plus average of elastic potential energy. That becomes 1 by 2 dm omega square s naught square. So then it's not too difficult to understand that from this now we need to understand intensity, which is 1 upon cross sectional area into energy propagated per unit time. So that will be 1 by A into this. Now dm is density into A into dx. So this further becomes 1 by A half rho into A into omega square s naught square into dx by dt. And dx is v dt, where v is square root of bulk modulus by density or square root of gamma t by n. The intensity you can see becomes half rho into v into omega square into s naught square. This is an easy formula to remember. If you recall, the power for a transverse wave, for a transverse harmonic wave, this kind of wave, y equal to a sine omega t minus kx plus phi. The power was given by half mu v into omega square into d square. So here mu is mass per unit length. So you replace that with density, which is mass per unit volume. So you divided the whole expression by area, so it has become intensity. And rest you can see the relationship is the same, that the intensity is proportional to square of amplitude. And you can also write the intensity as half square root of bulk's modulus into density into omega square into s naught square, where bulk's modulus becomes gamma p for gaseous medium. This kind of relationship. Yeah, so that is a theorem that average kinetic energy in SHM beta is half of the maximum kinetic energy. And average kinetic energy is equal to average potential energy. That comes from integration application. So if we integrate a sine square or a cos square function over time, this value comes out to be half. I mean, if you integrate it over time and divide it by a time interval, it comes out to be half. Just go through this section carefully once. Make a note of the basics. Okay. Now you don't need to memorize the derivation, because this will not be asked in your boards or anything like that. But you need to understand the process of the derivation so that you understand the logic of certain types of questions. And finally, for numerical problems, you need to memorize the formula. Okay, so further now we can also see the relationship of intensity with the pressure amplitude, because you can replace S naught with the pressure amplitude P naught divided by beta into K. So that also gives an interesting relationship. So you should know all these, sort of interrelationships between the various quantities. Like, you're used to V is equal to F lambda, and K is equal to 2 pi by lambda, these kind of relationships up till now. But now you should also be very familiar with all these kind of terms, how the pressure amplitude and the displacement amplitude are related for longitudinal wave. So P naught is equal to beta into K into S naught, and these kind of things, these kind of relations, E, etc. The equation for power itself, or the formula for power or intensity itself, whichever be the case. So you can also see here that using this, we can write intensity as half rho v omega square into P naught divided by beta into K whole square, which will give us this interesting relationship. Omega square by K square. That will become like a P square, P naught square. Now, V cube actually will become V square into V, I'm writing it as. Okay. Now, V square itself is, see that this will become half rho by beta square into Bulk's modulus by density into V into P naught square. So it becomes half V by Bulk's modulus into P naught square. And further, V can be written like square root of Bulk's modulus divided by density. So this can further be written as P naught square by 2 times square root of Bulk's modulus into density. So intensity can also be expressed in terms of pressure amplitude in this relationship. This Yeah, so Jagannath, that's right. So v square into v, I just kept it apart because I'm going to expand v square as beta by rho. Otherwise, I would have written it as v2. So remember that here, basically what I've done is omega by k is equal to v. So I substituted that omega square by k square as v square. Okay,
So could you scroll up for a moment?
yeah. So basically, you should know these final relationships, how intensity is dependent on S naught or how it is dependent on P naught. And you should also have a general idea of the process of derivation, like what all equations were used. But you don't really need to like memorize the steps of the derivation because you won't be required to do the derivation. It's just that you should know what all equations that you want.
Done, sir. Thank you. Done, sir.
Yeah. Now, next we will talk about loudness and intensity. Basically, when we hear a sound or perception of any sound, there are two things which become important: pitch, and the other is loudness. Now, pitch is a little bit more subjective than what we can define purely by a physics parameter. But pitch is more or less got to do with frequency. When we discuss about standing waves, I'll tell you what is the exact difference between pitch and frequency. But we can think that more or less approximately the pitch of a sound, that is whether it is very shrill or it is very low, that is to do with the frequency. Whereas the loudness is more or less got to do with the intensity. Why I'm saying more or less got to do with intensity is because if we compare a sound of a certain fixed frequency at different values of intensities, at different intensities, then we can definitely say that loudness is directly proportional to the intensity. For example, if we double the intensity of the sound or double the amount of energy per unit time per unit area coming from the source, but the source is operating at the same frequency, then to our human ear, it will seem like the loudness has also got double. Okay. But loudness perception varies with frequency also. And that is why it's not, it's not an exact statement to say that loudness is the same thing as intensity. Loudness has something to do with intensity, but intensity is perception. Uh, Intensity rather is a physical parameter, which is about the energy per unit time per unit area. Whereas loudness is about the perception of intensity also with respect to frequency. So our human hearing system, it is tuned in such a way that certain frequencies appear to be louder to us than other frequencies. So if we compare two sounds of the same intensity but of different frequencies, then one might appear to be louder than the other if it is within that region of frequency range which we are well tuned to hear, because our hearing system and the whole mechanism of our outer ear and the whole system of hearing, including the resonances that are created in the outer ear, and then the hammer anvil stirrup, the three bones that vibrate in our inner ear and all that, they're all tuned in such a way that a certain frequency range, which more or less falls in the 1 to 5 kilohertz category, that in fact it's like it peaks at around between 2 and 3 kilohertz. So those frequencies appear to be loudest. So, but loudest perception varies with frequency, in the sense that if we hear two sounds of identical intensity but different frequencies, then they may not appear to be equally loud. Humans perceive frequencies in the region of about 2 to 3 kilohertz with maximum loudness. That is just one general knowledge fact that you should know. So not that we will do any calculations based on loudness and pitch. We will do calculations based on frequency and intensity, but you should understand that how they're related to the quality of sound that you hear. So for example, if you are sounding two tuning forks, one is of about, let's say, 50 hertz, and the other is about 2.5 kilohertz or something, and both of them are sounded equally loudly, or I mean with equal intensity. So both are moving the same amount of air or creating the same intensity of sound waves in the air around it. But the one having 2.5 kilohertz will appear to be much louder to us compared to the one having 500 hertz, because our hearing system is tuned in that way. Whereas if you have two tuning forks of the same frequency, like 2.5 kilohertz, and one of them is sounded very with a lot of energy, and the other one is sounding softly. So definitely the one which is having more energy per unit time propagated, that will appear to be louder by proportion of the intensity of sound it's creating. So if we are equalizing the frequency of different sounds and then just observing the relationship of loudness with respect to intensity, there is a direct relationship. But generally speaking, if we are not equalizing frequency, we are hearing sounds of various different frequencies, then we cannot say that loudness perception is the same thing as intensity, because loudness also has some variation with respect to the frequency of the sound that we hear. That is the point I want you to understand over here. Now, as far as the human hearing range is concerned, so there are two things which are important in the hearing range for humans. One is the frequency range. So for sound to be audible, by humans, of course, varies from species to species. Okay, the frequency should be in this region, which I'm sure all of you know, 20 to 20,000 hertz. But for example, human voice produce sound in the region of about 1.5 to about 4 kilohertz. Doesn't really have so much of a range, but our hearing is much wider in range compared to what our own voices produce. For example, if you hear subway rumble, that is probably in the region of about 20 to 40 hertz. It's actually not really, it's perceived more from vibrations conducted to bones, not not heard so much by the ear. but something in the region of 50 to about 200 hertz. This is like the base frequencies. Heard by our ears from certain instruments or machines even produce engines, machines, etc. The kind of base frequencies that they produce. They have frequencies in that kind of region, like the double bass, orchestral music, or the lowest octaves, grand piano, or the sound from bass drums. They might have frequency components that are that. Yeah, sub bass also comes somewhere in this region. Whereas, as I told you, like voices, stringed instruments. I mean, even piano is stringed instruments, but stringed instruments like guitar, sitar, etc. Those kind of things. Wind instruments like saxophone, etc. They produce sounds in more of the kilohertz region. Yeah, so all this is part of the human frequency range of hearing, Saman. Okay, so I will not get into categories of frequencies, but, because like that is all very subjective also. Like it depends on what purpose you are classifying the frequencies for, whether you're doing it from you know scientific point of view or from point of view of how you classify sounds for, let's say, creating a library of sounds for film music or something. It all depends on those things. Okay. That is about the frequency range of audible sound. Now there is another thing which is important for perception of sound, which is to do with intensity and loudness. So the range of intensity for human hearing. So in this we have something called one important parameter. This is called the threshold of hearing. So this is the minimum intensity of sound audible to a human ear, and that is approximately 1 picowatt per meter square. Of course, this value that I'm giving you is subjective, okay, because each human being will have a different value. It depends on your body structure, the exact structure of your ears, and also how much damage your hearing system has undergone. Because right from the time we are born, continuously our ears are subjected to all kinds of noise and high intensity sounds. So by the time we come to early childhood or even a little bit later, most of us have quite a bit of compromised and damaged hearing systems. And that's nothing to be extremely worried about, but it's just that it's not what it's like exactly like when you were an infant. It's undergone some damage. So we don't always hear sounds that are that soft. Okay. Yes, we will talk about decibel scale also. That's a different scale of measuring sound. So in decibel scale, this value, threshold of hearing, is actually called 0 decibel, or it is calibrated as the 0 of the decibel scale. But in watts per meter square, the threshold of hearing is this much. Okay. And the other thing that we talk about is, again, this is subjective, okay, because again, it will vary from person to person according to their physiology. Okay, so this is called threshold of pain. And this is basically got to do with the fact that when we hear sounds of extremely high intensity continuously, it's not like you hear it for just a second or two, nothing is going to happen. But if you are continuously, like suppose you're working in a factory where some machinery is creating very, very loud intensity sound and you're not wearing proper protection for your ears, then continuously subjecting yourself will cause pain to your eardrums, to your ears, and eventually it will cause loss of hearing. So the pain actually
Sir,
happens because physiological reaction. Yes.
sir, but the threshold of hearing can vary from person to person, right? Or
Exactly. So
it is same for everyone.
this is a statistical average that is used as an engineering standard.
Okay, sir.
So threshold of pain similarly is an accepted value of intensity beyond which if we subject ourselves continuously to sound, then it can cause pain, and eventually continuous exposure can cause damage or loss of hearing, damage to our hearing system or loss of hearing. So that is called threshold of pain, and that is approximately equal to 1 watt per meter square. So all of us have at some point of time in our lives heard sound of much more intensity than 1 watt per meter square. But that will not cause pain or damage because we would have heard it for just a moment or two or a minute or something. If you're standing on a runway and an aircraft was taking off or landing a few meters away from you, or 200 meters away, you would hear sound, or you went to a loud factory or you went to a concert or something. But yeah, day in, day out, or continuously if you're working in an environment without any hearing protection, of where the intensity is consistently more than 1 watt per meter square, over a period of time, you will start experiencing pain in your ears and also eventually you will experience hearing loss. So that is the threshold of pain. So these two values are of importance when we talk about intensity of sound. Now, because you can see this variation of intensity is huge, from 10 raised by minus 12 to 1. So it's a whole range of million, 10 raised by 6 into 10 raised by 6, that's 10 raised by 12. So at an engineering level, and actually even for physics for that matter, I mean, at science and engineering level, we define a different scale for measuring the intensity of sound. And that is based on a logarithmic scale rather than a decimal scale. When we write numbers like this, it's based on decimal system. But we define a different scale for measurement of uh, loudness or intensity, which is called the decibel scale, which is based on logarithmic system. So next, let's understand this. So this is something important for us. Decibel scale or intensity of sound. This is also in short called the dB scale. Decibels is also used in electronics for analog signal intensities. But that will not be something we'll get into over here. That is something which you can later pick up at your engineering level. So for us, decibel scale is specifically for intensity of sound. So the intensity in decibels is just a parameter which is defined like this. It is 10 multiplied by a logarithmic factor with base 10 of whatever intensity of the sound is in watts per meter square divided by the threshold of hearing in watts per meter square. So we know that I naught's value is 10 raised by minus 12 watts per meter square. we use that. So for example, if the intensity in watts per meter square is, let's say, 2 into 10 raised power minus 6 watts per meter square. Now you want to convert to decibels. So you want to convert to decibel scale. Okay, then in decibels we will just write this as this value in decibels will become 10 log 2 into 10 raised power minus 6 divided by the threshold 1 into 10 raised power minus 12. 10 log 2 into 10 raised power 6 you can write as this. That will become 10 into log 2 is approximately 0.3 and log 10 is 1. You can see that this will become 63 decibels. So the intensity of that sound in decibels is 63 decibels. Yes, very good, Samad, that's right. Okay. So this is something that is important from both your board level type of exams as well as from your JEE mains and advanced. You should know the relationship of intensity expressed in decibels with respect to the absolute value in watts per meter square. Okay, so note this down and let's do a quick question. Express the intensity of 80 decibels in watt per meter square. Okay, Rakshit, I'll scroll up to that also. Yeah, I'll scroll up to this also. Okay, I'll scroll up to that. But this is like this very general information. You don't need to remember any of this or make it part of your notes. So let's come back to
Can you
this.
also show the loudness and intensity part? Yes, sir.
Okay, so let's come to this. So you will hear so this question. So here we can see that 80 decibels is 10 log I by amplitude. So this is the intensity. Now, a couple of more things to keep in mind about working with the decibel scale. The threshold of pain in decibel scale is 120 decibels. So in decibel scale, this becomes 120 decibels. Whereas I naught in decibel scale, threshold of hearing is 0 decibels. threshold of pain beta. We discussed this earlier. And another thing, 3 decibel rule. That is, if I2 in watt per meter square is double of I1 in watt per meter square, then I2 in decibels is I1 in decibels plus 3D. Or the inverse of this, that I1 is equal to I2 by 2 in watts per meter square. So I1 in decibels equal to I1 in decibels minus 3. This is very simple. I1 in decibels is 10 log I1 divided by I0 in watts per meter square. I2 in decibels is 10 log I2 by I0. So you can see that I2 in decibels minus I1 in decibels is equal to 10 log. So that is so this is our I2 in decibel scale minus I1 in decibel scale. From here you can see that if I2 is equal to twice of I1, then I2 in decibel minus I1 in decibel is 10 log, which is 3. And on the other hand, if for example I2 is half of I1, then I2 in decibel minus I1 in decibel will become 10 log half minus 3 decibel. That's how this EDB rule works. So it's actually nothing, it's just the application of the fact that log 2 is 0.3. But in engineering, it's a useful tool that people use. That if you double the intensity in decimals, if you double the intensity in watts per meter square of a sound or of a signal, basically in decibel scale, it's increasing by 3D. For example, if I1 is 80 decibels, I2 is let's say 89 decibel, then express I2 by I1 ratio in watts per meter square. So normally what we would have done, we would have converted this using the decibel scale method and seen how much I1 and I2 are in watts per meter square. But we can use the 3 decibel rule here. So we can see that 89 decibels is 80 plus 3 plus 3 plus 3. So we are adding 3 decibel 3 times. That means we are doubling it 3 times. So the value is double into double into double, 8 times. So whatever I1 is in watts per meter square, I2 must be 8 times of that in watt per meter square. Yes, very good. So that answer 8 is correct. So you can just understand it this way that 83 decibels is 2 times I1 in watts per meter square. So 86 decibels, that becomes 2 into 2 times I1 in watt per meter square. So 89 decibels. 80 decibel was I1. So I've done plus 3. So I've doubled it. Then again I've done plus 3. So I've doubled it. And then again I'm doing plus 3. Again I'm doubling. So every time I double the intensity in watts per meter square becomes 2 times. So plus 3 dB is equivalent to 2. It is 8 times I1. Now, another place where this becomes important is understanding variation of intensity with distance from a point source of sound. So variation of intensity with distance from a point source. So something actually doesn't need to be exactly a point source. This formula can be used in engineering just as a sort of empirical formula also. That if you have the source of sound like the cone of a speaker, and you're looking at distances which are quite large compared to the size of the cone of the speaker, you can treat it like a point source only. So if this is a point source of sound and it's creating sound equally in all directions, it's creating what we call radial pressure waves like this, radially symmetric pressure waves. Like you're used to drawing the electrostatic lines of force or electric field lines for a point charge, the same kind of geometry of these. So here at a distance r, what will happen is that the intensity of sound will become proportional to 1 by r square. So if S is a point source of power P in watts, then we say that at a distance r, the intensity of sound is proportional to that power, but inversely proportional to r square. More importantly, it's inversely proportional to r square. Now, what that factor is, it depends on various things like the absorption of the medium and losses due to friction and air resistance and things like that. Ideal case, the intensity would be power divided by 4 pi r square, but that would be in the case of idealized zero attenuation. The term attenuation in engineering means loss. So in real life, it doesn't happen that way. Attenuation is loss of energy in transmission of a wave. So in real life, it is more like some factor into P upon 4 pi r square, where K is a factor less than 1. But again, you can see the important thing for us is this thing. This is all like part of engineering, not in our syllabus. What is important from our syllabus point of view is this, that intensity is inversely proportional to square of the distance. So for example, if we say that the intensity of sound coming from a source is equal to 60 decibels at a distance of 20 meters from the source, then find the intensity in decibels at a distance of 40 meters or at a distance of 10 meters. If I go closer and I reduce the distance from 20 meters to 10 meters, then how much is the intensity I'll hear? Or if I go further away and increase the distance from 20 to 40 meters, then how much will be the intensity I'll hear? So quickly work this out with me. So you can make use of the 3 dB rule that we discussed about to make things simpler. So in watts per meter square, here, of course, when I'm talking about intensity, here intensity is in watts per meter square. We have to convert that to decibels. We are writing it in terms of power and distance. No, we'll use the 3 dB rule. Perhaps. Yeah, so 54 is correct. Okay. For our part A, that's very good, Devansh, and 66 is correct for part B. So you can see that at r equal to 40 meters, and say the intensity is I prime, it will be I divided by 4 because intensity is proportional to inversely proportional to r square. So this is in watt per meter square. Therefore, in decibels, it will become -6 dB. So it will become 54 decibels. So the thing is, knowing this rule makes this calculation much faster. Okay. You don't need to. The other way you could do this would be, okay, you would write I in watts per meter square is how much. So 10 log I by I naught is 60 decibels. So you would have found out from that that okay, I is coming out to be 10 raised power -6 watts per meter square. Then you would say that therefore this is at r equal to 20 meters. Then you would say that at r equal to 40 meters.
So it will be -4 decibel, no?
No, -6 because each time you make it half, it reduces by 3 decibels.
So we are only reducing it 2 times, no? One time.
But a double is not
one
equal
decibel.
to 2 decibels. Okay, doubling is equivalent to rise of 3
Okay,
decibels.
okay, yeah. Okay.
So the intensity in this will become this divided by 4. So it will be 10 raised to -6 by 4. 2.5 into 10 raised to -7 watt per meter square. Then if you convert this now to decibel scale using this formula, you can show that it will become this much. Ten log and so it has 10 into 6 log 10 minus 2 log 2. After doing all this calculation, you can come to this. But if you just remember the 3 dB rule, like the 3 decibel rule, that if you half the intensity, then there's -3 dB. If you double the intensity, there's +4 dB. So similarly, you can see for the B part, R equal to 10 meters. So the intensity at this will be the intensity at R equal to 20 meters into 4, because intensity is proportional to 1 minus. So therefore, the intensity in decibels will become whatever this intensity was in decibels plus 6 dB. So here it becomes 66 decibels. So especially for doing these type of questions, it's very useful principle to remember the 3 dB rule. So this completes the basic things about sound waves. Now next we will come to superposition of sound waves. So as usual, we'll start with interference. Okay, Jagannath, I'll scroll up. Okay. The first part we will look at is interference. So in interference, what is going to now happen is if we have two sources of sound, which might have whatever amplitudes, but they are having the same frequency. Okay, and we have an observer or a detector somewhere here, then the pressure waves which are coming from both of these are of same frequency and wavelength. So their superposition. So superposition of sound waves from multiple sources of very important identical frequency produces interference. Suppose this one is traveling a distance x1 and this is traveling a distance x2. So the wave from S1 that will be given by, let's say, some amplitude PA sine omega t minus kx1, and the wave from S2 that will create a pressure variation. Suppose this. So here PA and PB, they are the amplitudes, the pressure amplitudes.
Sir, it's same for like just like transverse wave, right?
Okay. And phi is the phase difference between the sources, if any. They might be synchronized also. And x1 and x2 are the path lengths. And of course, for both of these wave equations, omega is equal to 2 pi f, where f is the common frequency. K is equal to omega by v, 2 pi by lambda. And v is that square root of gamma RT by RT. So their superposition now will result in the same kind of phasor addition that we've seen earlier. Okay, so I'll just scroll up for a minute, go through the earlier questions solution, and then we will complete the equation for the interference. But you'll see that it's exactly the same thing that we saw for transverse waves. Or for that matter, even when we saw superposition of SHM, it's the same thing. So like the amplitude for the superposing SHMs adds by the phasor diagram method, or the net amplitude of transverse waves in interference adds according to the formula of that phasor method of superposition. Same way it applies here also.